Tut10. Good morning, good evening, everyone. If you're listening in the evening, good evening to you. If you're listening now, good morning to you. As I indicated on my email, today I'll be targeting to go through tutorial number 10, particularly from question number 10 to question number 20, basically question number 11 to 20, if I have to be precise. But my worry is, as could you see here, there are only 5 students who has attempted this module. I would have anticipated that more students has attempted it, but it's not the case. Only 5 students has attempted it. Anyways, I'll be going into it, and the questions that I'll be going through today is from question number 11 all the way to question number 20. If you see through, I just had a chance this morning go through the questions in case what they looks alike, and what I come up with is starting from question number 11 up to 20. It is mostly to do with heat and the temperature. Therefore, as usual, I'm going to bring up into my tablet and to write by hand in the strategy for this unit also, as it is the case the other before also. You have to read the question thoroughly, and then Caesar. Good morning, sir. Good morning. Can you hear me? Thank you. I want somebody, you just joining. I thought I'm only gonna be live from 12 on. That's why no students are here. But there is no load shedding, unfortunately. Therefore, I'm online. Let me share what I have here. Just hold on for me. This one, please confirm it to me that you see the screen I'm sharing. Thank you. Therefore, are you from PHYV or FVV? PHYV, great. Therefore, have you guys done from question 1 to 10 yesterday with James, or we don't know? Okay, bien, I will leave, you are still there. I will be starting from question number 11 today. Kind of slow today, but let's go together. It says 2 moles of an ideal gas. Before I start, just hold on for me. Let me check what the YouTubers are doing. Hi, just to say hi, because they don't have access to the chat. I'm gonna just start the chat here. Live chat. Hi guys. Just to start the conversation. Thank you for to be online, guys. Those of you on YouTube. I will be starting PHYV 101 tutorial 10, question number 11. That's where I am. And this particular question, it says 2 moles of an ideal gas, you could see there, are placed in a container of adjustable volume. You could change the volume according to what is given. Then it says when measurements are made, it's talking about the pressure is inversely proportional to the volume at constant temperature. The temperature is directly proportional to the volume at constant pressure. The temperature is directly proportional to the pressure at constant volume. Everything that is talking could be resolved. If you see what I'm having it there as on the screen, on the right side of the screen, those of you on YouTube also, and the Teams also. I forgot to start again. I'm gonna start recording in case somebody needed it. Start recording. Yeah, good. I've started. Those of you on the Teams also, on the right hand side, this equation is what I'm talking. If it is an ideal gas, I could use the PV equals to nRT. Okay, the pressure times the volume equals to nRT. This is ideal gas law, where N is the mole, R is a what is that? The ideality factor, and then T is the temperature. Therefore, from this equation, I could write that the PV over, no, this is not true. That equation is not right. I can't edit. Rather, this equation is supposed to be PV over T should be equal to NR. PV over T should be equals to NR. That means it is constant. I could write this one P1 V1 over T1 is equals to P2 V2 over T2. Just basically from that constant pressure P1 V1 over T1 is equal to P2 V2 over T2 because it is constant. Then let's work now here. In this case, in the choice number A, it says it's a constant temperature. If the temperature is constant, then you could write that T is constant, P1 V1 is equals to P2 V2. Okay, temperature is constant, T1 is equal to T2. Then you could see that if I solve for, I'm going to write it small, if I solve for P1, for example, P1 is equals to V2 over V1 times P2. See, therefore, the pressure at a given time, P1, we have to compare with V1. P1 is inversely proportional to V1. Then I could easily see that this expression is true then, because the pressure is inversely proportional to the volume if temperature is constant. Okay, that side is alright. Then I could also go that for the case of B, it says the temperature is directly proportional to volume at constant pressure. You have to look into this one. What does it mean? If pressure is constant, then I could write that I'm going to use exactly this equation again. If pressure is constant, I could see that V1 over T1 is equals to V2 over T2. This is constant pressure. Then I could see that the V1 is equals to, if I solve in this case, V1 is equals to T1 over T2 times V2. Then I could easily see that the volume is directly proportional to the temperature. You have to compare T1 with V1. Therefore, the temperature is directly proportional to the volume. This is also true. The third one, the temperature is directly proportional to the pressure at constant volume. Now, in this case, volume is constant. Therefore, I could write that the P1 over T1 is equals to P2 over T2 because volume is constant. This implies that P1 is equals to T1 over T2 times P2. Again, the pressure is also directly proportional to the temperature. This clearly indicates that the three expressions are true. The temperature is directly proportional to the pressure at constant volume, that's correct. The temperature is directly proportional to the volume at constant pressure, that's also correct. The pressure is inversely proportional to the volume at constant temperature. You have to be careful over here. What is constant? Here is the temperature, therefore pressure is inversely proportional to the volume. You could easily see there. Therefore, for me, this expression is, all of them are correct. If I go back to my everything, what I'm saying is this must be the correct. Probably yes, all of the statements above are found to be correct. That's correct. Let me just have a glance on YouTubers, what they're up to. Oh, YouTube is again having a problem. Sorry for those of you on YouTube. The internet is slow, but hopefully to resolve soon. Teams also. Still, students are still, maybe I must go slow. I said I'll be coming by past. Maybe I'll go back to it. He also, as I said, I had a time to sit and even draw this thing. Question number 12 is actually a very long question. Question number 12, it needs a lot of calculation here. but you could also answer without doing any calculation in principle. If I read through, it says a 100-gram cube of ice, it's an ice, is heated from this temperature, T naught is negative 120 degrees centigrade, to 120 degrees centigrade, now positive 120. As you see, it is started with that temperature at a negative 120, and then it ended up to positive 120 degrees centigrade. In which of the following process is the greatest amount of energy is absorbed by this material? Yeah, if it is me, I'm still slowly waiting for a student though. Let's discuss. If it is me, this is how I'm going to attack. Meaning, remember, whenever an object absorbs heat, its internal energy increases. That is my arrow. This is, for example, time as a function of temperature in degrees centigrade, my axis, time in second or something, let me say. Therefore, at t is equal to 0, my time is 0, it was ice, and it's negative 120 degrees centigrade. Then if you heat up with something, if you give a certain heat, Q1, for example, to the ice at negative 120 degrees centigrade, it goes all the way to 0. Nobody tells you about these two X lines. You must remember that the latent heat, meaning when the ice is heated, it undergoes a phase change at 0 degrees centigrade. This is a melting point of ice. That is the vaporization of water at 100 degrees centigrade. Therefore, this is what you have to keep in mind. You have to draw 0 and 100. What happened therefore is, if you give Q1 for this at this temperature, it will raise to a certain 0 degrees centigrade. Then once at 0, it will undergo a phase change. Remember this one, Q2 is actually latent heat of fusion, LF. I hope Professor Tim took you through. And then once it becomes liquid, Q2 is latent heat. It changes it into liquid at a certain time. Now the heat has to be supplied to the liquid. Q3 is basically to boil the water. And then the moment it reaches 100 degrees centigrade, it undergoes another phase change. This is latent heat of vaporization, LV. And then beyond that, if you continue heating, it goes into steam. STEAM. That's the process. The question is, where is it need a lot of energy? Is it going to be Q1? Is it going to be Q2? Is it going to be Q3? Is it going to be Q4? Or is it going to be Q5? And then, if you don't know of, how do you know even? How do you start? Warming ice to melt the point. For example, the selection says warming ice to the melting point. Basically, this is warming ice to the melting point is Q1. I could write this one as a Q1. Melting the ice to become water. This is Q2. And then warming the water. What's that? Warming the resulting water. That's Q3. And then vaporizing the water to become steam. This is Q4. And then heating the steam. This is Q5. Which one takes the highest heat? YouTubers, sorry guys, again, the internet says YouTube is not receiving enough video to maintain smooth streaming, but hopefully to resolve soon. Those of you, thank you for liking also. Hopefully to resolve soon. Let me, by now I'm expecting a student to join me. Pungasisa, are you still there? What do you say about this particular question number 12? Which one is going to be the highest heat? Do you have idea even? What I mean is, did you guys go through such a drawing in the class? Like from a certain, especially for ice, heating and a cooling curve. This thing is called heating and a cooling curve. Did you go through such? Zamile, thank you for coming in. Did you go through such heating curve? Anyways, if you heat up an ice at a negative degree centigrade, it will absorb heat. My question to you is, do you know that Q2 exists, latent heat of fusion? Ngaziza, you're disturbing. Yeah, let's continue then. For me, without doing a calculation, you could understand, by the way, the greatest amount of energy is actually absorbed as Q4. If you ask me why, that's steam. Steam, latent heat of vaporization, LV. For water, L fusion is 334,000 joule per kilogram. And then latent heat of vaporization is 22,600. What is that? 220, 1,000 again. Joule per kilogram. The latent heat of vaporization of water is so strong. In other way, steam burns you more. Without calculation, if you know of that steam involves a lot of heat, your answer would be Q5. But can we get in terms of number though? Can we calculate this? Remember, it's 100 gram, meaning 0.1 kilogram of ice. We're heating from there to here. I've just put together here. Let me take you through. This is zero is missing here. 260, there is 1 0 there. To write. This is wrong. 260,000. That's the latent heat of vaporization of water. Therefore, if you follow this diagram, Q1 is MC delta T. I hope you guys, I know by now you must be under. I'm going to change the pen. Hopefully, I'm expecting you guys have learned it through this one. Heat is MC delta T. Please, those of you whose your mic is still on, would you mind to switch it off, please? If you don't have question, unless you have a question, please switch off your mic. Q1, let me go through. Q1 is basically, Q1 is equals to mass MC of the steam, ice, delta T, MC delta T. M is 0.1. I just put a number here. I have scratched it with a pen on my paper. This is 0.1 times 2090. That is a specific, what the C of the ice. You could see that this is the ice is 2090. Delta T is going to be from or 0 minus, let me write here. Delta T here is 120. Delta T here is 0. Therefore, delta T here is 100. Delta T here is 100 to this is 20. Therefore, let me see delta T times 120. I got this one, Q1 as 25080 joule. That's Q1. In the same way, Q2 is equals to, is a latent heat. Therefore, Q2 is M times L fusion, LF. If you do this one, 0.1 times 334 times 1,000, I got this one as 33400 joule. This is Q2. Q3, I got MEC delta T again 0.1 times, remember this one C of water. This one is a different, because it is water now, you should not use at Q3, you must use C of water. Be careful there. C of water delta T is again, what I say, 100 times 100. I get for this one as 41800 joule. Then I don't have a space now to write. I'm gonna just write here Q4, which is highest, is 0.1 times 2260 and 1000, which I get about 226,000 joule. You see, this is the highest heat. And then Q5, which is mass C of steam, forget the careful here also, C of the steam. Let me write in different page. This is steam, STEAM delta T, which you get this one as I got around 4020 joule. Therefore, the highest heat basically is when we use that Q4 is the highest. Or if you don't do the calculation, I'm going back to where we started, you don't need to do even a calculation. If you know of that steam requires, or steam carries a lot of heat, or the latent heat of vaporization of water is the biggest. If you know that one, you could easily answer. Maybe if I move around, admit somebody's waiting. If I move around, we will pick it up. Let's see, it's more or less it's the same question though. I will spend a little bit time. What is question number 14 also? It's the same, kind of the same. Therefore, if you miss the question, the remaining questions, you're gonna catch us anyway. My YouTubers, how are you doing? Yeah, my YouTubers are a little bit better now, but I lost connection in between. Oh, it is back though. Question number 13. Guys, those of you who just joined me on the Teams, I just go through question number 11 and 12. If you want me to go back to it, please don't hesitate. But anyways, what we did with question number 11 is just to bring you in. It was ideal gas law. You simply use the ideal gas law, whereby PV is equals to nRT. If you use that one, meaning now that means you could write P1 V1 over T1 is equals to P2 V2 over T2. That's the main one. In the case of A, constant temperature. If temperature is constant, that means P1 V1 is equals to P2 V2. Then you will see that the P1 is equals to V2 over V1 times P2. You see, the pressure is therefore is inversely proportional to the corresponding volume. The answer is, we said this is correct. Then for the second round, for part B, it says the temperature is directly proportional to the volume at constant pressure. You have to keep that one in mind, constant pressure. Therefore, if pressure is constant, V1 over T1 is equal to V2 over T2. Then if you solve for V1 is equals to T1 over T2 times V2. I'm just solving from that equation. You could simply see that the volume V1 is proportional to a temperature T1. Proportional, directly proportional. Therefore, this is also correct. And then the last one is what happens if it is a constant volume. It says for constant volume, you just use again the same equation. P1 over T1 is equals to P2 over T2. Then if you solve for P1, it's going to be T1 over T2 times P2. You could see that the pressure is directly proportional to the temperature. Therefore, we said the three given conditions are true. A, B, and C are correct. That's what we did on question number 1. On question number 2, it actually says and ice is heated from negative 120 to positive 120. And what we did was to go through step by step. What you should remember is when you do such a thing, remember the ice undergo the melting at 0 degrees centigrade. Therefore, that involves latent heat. This is called latent heat of fusion, where that value is 334,000 joule per kilogram. Then if you continue heating the ice, it become water already, and now Q3 is the water, but if you continue heating the water, it vaporizes. At 100 degrees centigrade again, there is a phase change. That phase change is latent heat of vaporization. You continue heating. Therefore, I said warming ice to the melting point, which is Q1, melting ice to become water, which is Q2, warming the resulting water, which is Q3, and then vaporizing the water to become steam, Q4, and then heating the steam, which is Q5. You could calculate Q1, Q2, Q3, Q4. We go through. Q1 is mc delta T, remember that time it is ice. And then Q2 is M times LF, that is a latent heat of fusion for Q2. And then this is a value I got. Q3 is water, don't forget that one. Therefore, the specific heat capacity you should use is that of the water. I put for you there. That of the water is 4180 joule per Kelvin per kilogram. If you put inside, this is what the value you get for Q3. Q4 is mass times latent heat of vaporization. This is the biggest we get inside. And then Q5 is you heating up steam. Remember, the only thing you don't have is delta T. For Q1 is 120. For the Q2, there is no delta T, obviously. For Q3 is 100. For Q5 is 20 degree or 20 Kelvin or 20 degrees centigrade, because we just the difference is doesn't matter though. If you put together, therefore, we got to the point that the highest heat is actually Q4. Therefore, your answer must be D. And then, I didn't go back to it even and click it. Therefore, the answer should be D. That's how far we go. Okay. Question number 13, which I'll be on, is about, where is this one? Question number 13 is here. It says, it's you as a student, a 100 kilogram student, eats 200 calorie donut. Oh, a lot of it. To burn it off, now you wanted to burn this thing. He decided to climb the steps of a tall building. How high in meter would he have to climb to expand an equivalent amount of work? Expend an equivalent amount of work. But for me, it was easy. I just said the energy that this guy must spend must be equal to mgh, where this mgh is a potential energy because of climbing. Then the height he has to climb, therefore, is basically the energy that he took in, which is 200 calories, divided by mass times gravity. If I just put together this one, the height must be, therefore, the height must be also scratched by paper, 200 calorie. You must change this one. Don't forget that one. What is 1 calorie? Basically, 1 kilocalorie equals to, this one is what you need to have, 4180 joule. That is a kilocalorie basically. Therefore, 200 times 4180 divided by what is that? mg. M is 100 times gravity is 9.8. If you go like that, I think it's easy. Therefore, it's a 2 times 4180 divided by 9.8. I scratched that. I got about 853 meters. You must climb. If you have eaten a donut that has got 200 calories, you must climb a building which has got 850 meters, but there is no such building around though. Yeah, that's therefore the answer should be 853. That is what I get. Where is 800? Oh, maybe they use some sort. I don't know where I made a mistake, but I see something close to 854. Let me just go click onto it. 854 maybe. This should be correct though. Yeah, that's true. Then should I hold on in case you guys, are you okay? My teams, are you alright? Are you following? Thumb up, thumb down. I also want to check what is going on with the YouTube's. This YouTube is in trouble. I still have a warning that the streaming is good. At least the connection is good. Not excellent, good. Good. Guys, if you have questions, please don't hesitate to push me. Here, question number 14 is basically again heat loss, heat gain. For me, this is typical first law of thermodynamics. It says a 5-gallon container of water, and I hate this sort of question. The gallon is in American, degree Fahrenheit is in American. The questions are not edited. I don't like it, but yeah, 5-gallon container of water. It is approximately 20 kilogram. I put for you here. Is the temperature is a 212 degree Fahrenheit. You could convert into it. That 212 degree Fahrenheit is about 100 degrees centigrade. That is a hot one. I'm thinking on the top. The mass is 20 kilogram. Now you have to add it to 50-gallon tube, approximately 200 kilogram. This is hot water. That's what I'm looking there. This is a cold water. Then I'm going to add the hot water to the cold water. Therefore, they will reach a certain final temperature. Basically, it's very, very simple. Energy is conserved. Q1 plus Q2 should be equal to 0. Heat gain equals to negative of heat loss, basically. I know Q. Therefore, for the first one, it's just a water. Then I'll simply write the mass of the hot water. Let me call it the mass of hot water. C of water. Delta T should be T, it's starting from there in the 2 final, T final minus 100 must be equal or plus mass of cold water, C of water, into the final temperature is going to be T final minus 10 must be equal to 0. Basically, this thing is, I could remove the specific heat capacity of water on both sides. Then you could simply put it in 200, which one is which? Okay, 20 kilogram into T final minus 100 plus 200 T final minus 10 must be equal to 0. Solve for T final, basically. Okay, if I remove by this, what do I get? That 0 go, that is 1, that would be 10. I could write that T final minus 100 plus 2T final minus 20 must be equal to 0. Then what do you get? Do you have another page? I don't have. I must finish it here. Then if you see, what is that? That is 10, not the 2. Made a mistake, guys. Stop me, please. I'm gonna zoom a little bit like this so that I'll have a place to write. 2. Let me write with a very, very thin pen. What I get? That 0 go, that 210. Yeah, rather T final minus 100 plus this is divided by 2, that is 10. 10 T final minus 10 times 10 is 100, I believe. No, is it? No, that's 10 times 10. Equals to 0. This implies, what do I get? Minus go positive. 11 T final is equals to 200. Therefore, T final must be 200 over 11. What is 200 divided by 11? I didn't do here. Is equals to 200 divided by 11. I got 18.18. Basically, in degrees centigrade, I got T final to be, or I'm gonna write it here, 18.18 degrees centigrade. I believe this thing is very, very easy. Therefore, if you have question, please stop me. What I did here, 18. Answer should be correct. Yeah. What I did here, if I just go back to what I scratched, because you guys, you are not interacting. I don't know now if I've done it properly. What I did here is, when you mix hot and a cold object, they will have a final temperature T final in between. Then the hot object must lose heat, the cold hot object must gain heat. Therefore, Q1 plus Q2 must be equal to 0. Energy is conserved. I put everything on for you on the board. Q1 is MEC delta T. Q2 is also MEC delta T, but the masses are the one that is different. Both of them are water, therefore you could cancel C. Then I using that one, which I get is basically 20 into T final minus 100 must be equal to negative of, if you are writing that side, heat gain is equal to heat loss, negative of Q2, which is 200 into T final minus 10. Heat gain equals to negative of heat loss, or this expression, if you are used to that one, Q1 must be equal to negative of Q2, where Q1 is a cooler one or hotter one, it doesn't matter. In this case, you can exchange up and down. Then I get these things, this one, T final is 18 degrees centigrade. That is what we get. I don't know if this thing is not just boring though. The same here. Question number 15, also almost the same. It says a 5 kilogram piece of lead, at least it's different now here, with a specific heat capacity of 0.03 calorie per gram per degree centigrade. This is a very bad unit. You must convert it to the appropriate unit. I've done it here. Having a temperature of 80 degrees centigrade is added to 500 grams of water having a temperature of 20 degrees centigrade. The same is true here, but it's lead with water. Then Q, as usual, is MEC delta T. C of water is 4180 joule per Kelvin per kilogram. That is you should be aware of this one, or you will be given. C of lead, I've converted for you, calorie per kilogram, calorie per gram per degree centigrade to joule per kilogram per Kelvin. Please find out yourself if you don't know how, but this is the inappropriate unit for the lead. Then I've converted, you don't need to if you don't want. You don't need to convert into Kelvin. You could continue working as it is, but because of the Kelvin under, it is better to work with Kelvin in SI unit. I've converted for the lead. It's a 5 kilogram, is it? A 5 kilogram, yes. Temperature of 80, which is 353 Kelvin, and then the water is a 0.5 kilogram, yes, which is 500 gram, a temperature of 293. If you mix again, the final temperature is somewhere in between. In the same way, Q1 plus Q2 is equal to 0. If you put together, this is exactly what I have. Then if now I put the number as I did for the other one, then basically I'm going to say mass of the water, specific heat capacity of the water, delta T for the water must be, or plus mass of the lead, C of the lead, delta T of the lead must be equal to 0, where L is lead, W is for water. Then the mass of the water is 0.5. C of water is already, we know, 4180 times 4180. Delta what this one, delta of the water is T final minus where the water is, T final minus 293, plus the other one is with mass is 5 times the specific heat capacity. Now we change it, 0.458 into T final minus the initial temperature of it, which is 553. $335. Somebody is, please, when you join, would you please switch off your mic? Andy, I muted you. Okay, please, those of you who just joining, please would you mind to switch off your mic as we join in minus 353. If you solve this one, everything is there. Solve for T final. What I get is, if you go through this expression, basically you have got 0.5 times 4180 into T final minus 293 plus 5 times 0.458 into T final minus 353. Solve through this one. I don't know. T final, according to this expression, I got 293.067 Kelvin. Solving it. 293. That's what I get as a final temperature. Convert it back to in T in degree centigrade. Therefore, T final in degree centigrade must be equal to whatever you have. 293 minus 273. I got close to 20 degrees centigrade. That's what I'm getting. Therefore, the final temperature of this system is about 20 degrees centigrade. It should make sense though. If I go back, this one is at 80, this one is at 20, then the mass of this one is too small, and the specific heat capacity of the water is that much big compared to the specific capacity of that of the lead. Therefore, the final temperature is actually, the lead didn't change anything. It almost didn't do any effect. What it means is, let me go. What it means is getting 20. First, let me check if I'm correct. Uh-oh. Hey, I'm wrong. What did I make a mistake? Hey? Something is wrong. That means I have to do. That means I have to do. I don't know. Okay, let's do. What I mean is, this is wrong. I have to go through. My handwriting is not good there. That's the temperature I got. But let's do this one with the Excel. Q1, if I say that one is, I'm gonna do it by number. Delete this, hopefully everybody can see. I'm gonna increase this to big, 48 equals to 0.5 times 4180. I got this much, 2020. Therefore 2020 into 2090 rather, 2090 into T final minus 273 must be plus 5 times, the other one is equals to 5 times 0.458. Go to 48 also. 2.29 into T final minus 353 must be equal to 0. Then 2090, I will bring this one now, sorry. This is what I wrote, 2090 T final plus 2.29 T final must be equal to, I'm taking that side, 2090 times 273 plus 2.29 times 353. Then this one is 292.29 T final must be equal to, what is this one? 2090. I'm going to go back to my Excel. This one times 273 times that much is this much. I'm gonna get, what is that, 57. I'll show you now what I'm writing. 0570 plus this one times 353 enter. I got 880, 808, and then if you add up the two of them, is equals to this one plus that one. I'm using this one now. I got, I'm gonna make this one all big. Take to 48. Then this one also take to 48 is equals to this one divided by 292.29. The answer is did I make any 2090 293? Did I make any mistake? My head is upside down today. Guys, help me. Did I make any mistake there? What I've been doing is, I'm gonna bring it here. Basically, mass of the water, specific heat capacity of the water, delta T of the water plus mass of the lead, specific capacity of the lead, delta T of the lead must be equal to 0. Mass of the water is given 0.5, specific heat capacity is given. We know of basically T final minus 293 plus 5, the mass of the lead, specific heat capacity of the lead, times T final minus 353. This must be equal to 0. I must write it here. This must be equal to 0. Then what do you have is, I've got the multiplication between these two is 2090, T final minus 273. The multiplication between that and that, I got 2.29, which equal to 0. If we resolve that way, what I get here is 2717. And that's how far I could go, but I don't like what I get it here. Just finish for me this one, and then the final temperature with this method, if I use my calculator, I don't want to go up and down with the Excel now. I'm gonna use, I got 306 T final using this one, 306.85 Kelvin. This is, this makes sense a little bit. T final, therefore, whatever I get now, 306, I'm gonna forget about that, or 07 maybe, 307 minus 293, maybe you get 34 here, yeah, degrees centigrade. That is better. That's better. Therefore, you see, I was wrong. The answer is 34. It's correct. Therefore, it's my rushing. Sorry about it. We'll get again here though. I think I finished. I want to go back. Please consider this one. Let me just spend a bit because I made a mistake. What you should be doing in this case is basically understand the question. You have got a cold object, you have got a hot object. When you mix up hot and cold object, heat gain equals to heat loss, negative of heat loss. Who is gaining heat, who is losing heat? Just use the formula Q is equals to mc delta T. Don't forget C is the specific heat capacity. Delta T is T final minus T initial, basically, where it is coming, where it is going. If you put that equation together, you should simply use that Q1 plus Q2 is equal to 0, where this Q is, I'm going to put it here, Q, come on man, Q is equals to mass of the lead, C of the lead, delta T. Here, Q equals to mass of the water, C of the water, delta T. Then just use Q1, let's say this one Q1, let's say this one Q2, Q1 plus Q2 is equal to 0. The unknown thing in this equation is only the T final. Therefore, solve for T final. I'm basically done with this sort of equation here. Going, let me check what these YouTubers are doing. Oh, still the YouTubers are struggling. The internet is bad at university today. Okay, let's go. Question number 16. Says a child has a temperature of 101 degree Fahrenheit. Again, it's a degree Fahrenheit. Please use that conversion again into degree centigrade. Basically, I want to go there. Didn't I put it here? Yeah. This temperature is 101 is is 38.33 according to my conversion. This one is 38.33 degrees centigrade, and T2, which is 70 degree Fahrenheit, this one is about 21.11 degrees centigrade. That just convert. Then the question is, find the energy loss each second in watt due to radiation, assuming the emissivity of 1. I don't know if you guys know of this formula. Are you used to this thing? Have you covered in the class about it? Heat per unit time, delta Q by delta T, is given by emissivity times the cross-sectional area, sigma, A T raised to 4. This is not the cross-sectional area in principle, sigma. It's in watt per meter square per T raised to 4. So that this thing is in joule per Kelvin. I just put a number together though. Delta Q by delta T, use this formula. Sigma is this much for human being. Sigma for human, this is a child. Maybe the question is also not good. It doesn't specify sigma there, but you could use sigma as 5.67 times 10 raised to minus 8 watt per meter square per Kelvin raised to 4. This is amount of heat. If I think of it as a power per area per T raised to 4. Emissivity is 1. The area of a child is given. It is 2 meters square. T1 is that much. T2 is this much. Basically, delta Q by delta T is just put this number together. What I get is, if you put together, I get delta Q by delta T equals delta T times T should be equals to 5.6 times 10 raised to minus 8. By the way, this one T1 raised to 4 minus T2 raised to 4. I got about 1.19. That's what I scratched on my paper. Times 10 raised to 9 times the area is 2. Therefore, I got this one about 217 joule per second. That's my number. But basically, the question is about knowing the formula and also knowing about the sigma of a human being. Hopefully, you guys will pick up. Therefore, the answer is 217. Maybe I'm wrong. Let me go check again. 217. I didn't check this one. Yeah, that's at least correct. This one is wrong. It says 34. We know why it is wrong. Oh, question number 17. See, question number 17. It's missing. I better use. I just had a time. Therefore, this is what it looks like actually. The graph which is missing is this one. It's a pressure in atmospheric pressure, P, along the y-axis. This is the y-axis. That is the pressure. And then this is a volume along x-axis. That is what is missing here. If you are trying by yourself on a Moodle, please just, this image is, I want Pro team actually to correct it. It's basically, this is a given graph. It's A and the B. You could see that at point A is highest pressure, 6. The volume at that point is 2. You could see that A is, x-axis is 2,6. Point B is, the coordinate for point B is 8, x-axis 8, 2. Pressure is 6, and the pressure is 2 here. Volume is 2, volume is 8. Then I just sit it, when I was looking into the question, I said, okay, using first law of thermodynamics, what should I use? What I'm looking for is the change in internal energy. That is where the question is. The change in internal energy of the gas in joule, he asked me. Then I say, okay, delta U, the change in internal energy is equal to delta Q minus work done. I hope you have done this in the class also, which is supposed to be the case. This is a formula that you should be knowing. Okay, that formula. Delta Q is given. It is expanding. Heat is taken in during the process, which is 1.02 times 10 raised to 6 joule. I've got heat delta Q, but I don't know W. That's what the question is. But the work done is force times distance. I'm just sitting here and kind of deriving an equation. Work done is equal to force times distance. But I know that the pressure is force over area. Therefore, instead of F, I'm using PA times D, where D is the work done, whatever the force is done. But if you see area times D is, or length is a volume, the work done therefore is equal to PV. If you don't know this one also, the work done is given by pressure times volume. That means I say the work done in this diagram, it's a pressure as a function of volume, it's an area under the curve. If you see that area is kind of area of a triangle. It's area of a triangle, whereby I could see that this is like this, which is a, like that. This area for me is base times height, half times base times height. I said, okay, if it is a triangle, I simply say half times base times height, which I get about 12 atoms per meter cubes, because the pressure times volume. But if you convert into, it's given that 1 ATM is 1.01 times 10 raised to 5 Newton per meter square. If you put together that, the work done is actually this much. Okay, this much. If you put together now delta U is equal to whatever you have there, 1.02 times 10 raised to 6 minus 12 times 1.01 times 10 raised to 5. This is the pressure I got, which is 1.92. Do I have anything here? You see, I checked this one actually. I checked on the internet, or not on the internet here. I don't have my value here. Maybe the diagram displayed here is different from what I'm using, but I'm hoping that it's almost the same sort. Therefore, for me, this is good enough, even though I don't see the answer here. The only problem then is, what is the diagram shown in the equation? If the diagram is known, basically you simply find the area under the curve, whatever the number is. You see, if the 6 and the 4 is different, 6 is for me, the base is 6, which is 8 minus 2. There is 6. This one is the y-axis is 6 minus 2, which is 4. That's where I have base times 8, 6 times 8. 6 times 4. Maybe if you're thinking, where did you get 6 and the 4? Is 8 minus 2, which is 6 along x-axis, and then 6 minus 2, which is 4 along y-axis. If your diagram or whatever Professor Tim has provided has got a value different than what I have, of course the work done is different. Please just convince, but the calculation is correct. So far so good. I don't see any question. Push forward. I didn't say it today, but I was sick, by the way, when I'm coming to university, kind of so slow, and still you could see that I'm wobbling around, but I wanted to finish because this is the last tutorial. I'm sick like a dog in principle. I didn't want to go out of the office. Just sitting in the office, I don't want to interact with people in case I'm such contagious. Therefore, if you're losing the usual energy that I used to teach, because I am actually trying to fit into today's day, even though I'm so weak. Okay, let's go. Hey, it says an aluminum rod 1 is 1 meter long with a cross-sectional area of 2 centimeters square. Aluminum rod 2 is 2 meter long, the length is 2, the cross-sectional area is 4. Aluminum rod number 3 is 3 centimeter long and the cross-sectional area is 9 centimeters square. If each rod has the same temperature difference applied across this end, which rod has the greatest rate of transfer of energy between the ends? You see, but I just used my knowledge of delta Q by delta T. This is a formula you should be looking for. Delta Q over delta T is K, the rate or the material related, the conductivity of that material, K, A per unit length times delta T. You see, delta Q by delta T is proportional to area by length. from that expression. What I want is, the question is, which one transfers the heat quickly? Then for rod number 1, A over T is for 1. A over D is basically, A is, says 2 over 1, which is equals to 2. For number 2, rod number 2, let's say like number 2, A over D is equals to, what is the area? For rod number 2, aluminum rod number 2 has got 4 divided by 2, the length is 2, again you get 2. Is it true? What did I say? Get 2. And then for number 3, again, A over D must be equals to 9 over 3, which is equals to 9 over 3, which is 3. Therefore, I believe the ones that transfer the heat very fast is the third one, because it's the rate at which heat transfer is A over L. Just knowing this one will give you that the ratio of area by length is what matters here. As long as K, all of them are aluminum, therefore K is the same, delta T is the same. It says the same temperature is applied across the index. That means delta T is the same. What matters is area divided by length. For rod number 1, area is 2, length is 1, I got 2. For number 2, am I right? Yes, 4 divided by 2, which is 2. For number 3, 9 divided by 3, which is 3. Therefore, this guy must be the one that takes heat very quickly. Let's go check. Is it the third one then? I said 3. Please don't make me struggle. Yeah, 3 is correct. Excellent. Question number 19. I just wanted to finish and disappear now. Question number 19, it says an 8,000 kilogram aluminum flagpole 100 meter long is heated by sun from a temperature of 10 degrees centigrade to 20 degrees centigrade. Find the work done in joule by the aluminum if the linear expansion coefficient of aluminum is, by aluminum, if the linear expansion coefficient of aluminum is 24 times 10 raised to minus 6 degree per degree centigrade, that's that one. The density of aluminum is given, and then basically the pressure is 1 times 10 raised to 5 Newton per meter square. Pressure is also given. Then as I was sitting here, I said, okay, what am I looking for? I'm looking for find a work done. Therefore, I said W, the work done in such condition, is P times delta V. Remember, volume expansion and length expansion, you have done this one, whereby delta L, remember, delta L is equals to L naught alpha delta T, delta V is equals to V naught beta delta T. You have done this one in the class, I am sure. Therefore, I'm going to just use that one for delta V. B, this one is B V1 delta T instead of B. Remember also here, B is 3 times of alpha, because what I'm given is only the linear thermal expansion. It's not volume, it's linear. But if of course you remember that along X, along Y, along Z, alpha, 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 all the same, that's where the 3 is coming. Basically, beta is equals to 3 times of alpha. Instead of volume, because volume is not given again, I'm making an equation. Because volume is not given, I'm using, because there is a mass, there is a density, instead of volume, I use M over rho. Or that one is density is equals to mass over volume. This implies that the volume is equal to mass over density. That's what I've used today. I've got my everything then. Pressure is there, this is there. Therefore, the work then must be equals to 1 times 10 raised to 5. I know the units are all right. I'm just going to continue in times 3 times 24 times 10 raised to minus 6. This is 3 alpha. M is the mass is 1000. The density is given, which is 2.7. 2.7 times 10 raised to 3. This is a volume. Delta T is 22, that's 10. If you put together this one, I've scratched on my paper also. I'm not going to do again. I got 213 joule. 213, it's exactly, she's sitting there. I'll see that it's 213. Hopefully it is gonna say yes. Yep. Oh, so tired. If it says no, I'll go back. That last one. Oh, no, I can't tell you how much I'm tired now already. The last one, I also put that one, and because I'm so tired, I don't know if you guys even know this question. It's a slab of concrete and the insulating board are in thermal contact. You bring them and they put in thermal contact with each other. The temperature of the outer surface are 68 degree Fahrenheit and 50 degree Fahrenheit. The temperature of their outer surface inside is basically, okay, there is a temperature difference. Determine the rate of heat transfer in BTU. I said, what is BTU now? Per feet square per hour. This is copied from America. That's a problem. What is that? BTU. What is BTU? You see? British thermal unit. What is that British thermal unit? A measure of heat content of a fuse or an energy source. It is a quantity. Yeah. Anyways, forget about that one. I put together just a simple number. And I don't know if you know of this formula. Also, this is the temperature of the outer that determine the rate of heat. Somebody want to have a question? I see a sound. Okay, let's go back to it. The temperature of the, what am I reading? Determine the rate of heat transfer. That's what I mean. The rate of heat transfer, P, I call it P, whatever you're going to use it, is given by A, the area of those in thermal contact, times T high minus T low. Of course, there is a heat diffusion between the two slabs or the two objectives that is being heated, divided by the R values. You see, this thing is, what are the R values? And it's given that what is this R value for a slab? I don't know, because this thing is, I'm not engineer. What is R value? You see, an R value tells you how well a type of insulation can keep heat from leaving or entering your home. Basically, this is what the expression looks like. I put together anyway. You have got two R values for it. If you use this one, therefore that rate P, which I'm putting together, must be equal to the area, which is A, into the 18. That's the difference between, just take the difference between 68 and the 50, which I get 18, divided by 1.93 plus 8.7, the given ones. If you see, therefore I see this one is about 1.69A. Therefore, you see that in terms of this one, it is going to be about 1.7 in terms of P over A, basically, if you take it out. Okay, the rate of heat transfer between these two things is about 1.7. I don't know if this thing is interesting. I don't think so, but the answer is 1.7. Hopefully it's not gonna make me spend time. Yeah, 1.7. Guys, I put together myself basically today, even though so tired, so sick. This is all what I have wanted to cover. If I become too slow, sorry about today's class. And basically I wanted to cover. I am pushing myself actually to cover. Please go through. Those of you on the YouTube, thank you for joining. Yeah, still with warning. Thank you for joining. And yeah, next week probably I will see you in class. If you have a question, guys, you can come in class, because we will be finishing class. We will be coming as a tutor. All of us, or some of us basically, during the class time, you could have a chance to ask us a question. With that notes, I wish you all the best. I'm gonna leave you now. I'm gonna stop sharing. I'm gonna stop recording. And yeah, stop recording. Yeah, bye bye. I'm gonna end this one also.